Welcome back to Introduction to CFD, Computational Fluid Dynamics. I'm Professor Steve Miller. Today we'll be talking about our continuation of turbulence and turbulence modeling. We'll look at particular compressibility effects in turbulence and how they'll be implemented, of course, in the RANS-based models. In the previous class, we finished introducing our RANS-based modeling approaches, which we'll heavily use in this particular class. We looked at, of course, one equation and two equation models, which, as you remember, represent one and two partial differential equations within the equations of motion. Then we talked about the turbulent energy equation. This is a trace of the Reynolds stress equation. Then we derived two important one equation models, the Baldwin-Borf model and, of course, the Spalart-Armaris model. We'll try the Spalart-Armaris model in this class. Then we looked at famous two equation models, and there's two major categories. Both have the first equation as turbulent kinetic energy, and the second equation as dissipation or specific dissipation as epsilon or omega, respectively. There's other two equation models, and we looked at closure coefficients and a few applications. You'll have noticed that many of the formulations of the classic models were done in the incompressible regime. Now, there's two ways to proceed if we care about compressibility, especially in a turbulent flow. The first, of course, is to try and include some sort of corrections to the baseline models. This is a very popular approach. The second approach is trying to include compressibility effects from the beginning, which is probably more mathematically rigorous. This will require a new type of averaging called Favre-Averaging. It's nothing but mass-weighted, and we'll derive the mass-weighted equations of motion using the Favre-Averaged approach. We'll also look at the certain physical considerations that are required when looking at a flow which has compressibility and turbulence. We'll finally look at a few turbulence closures that involve the compressibility effects, and then we'll look at some particular applications. You'll see that in contemporary CFD codes, often turning on and off compressibility effects for every type of turbulence model is nothing more than a click of a button. There may be no setting up whatsoever for some models because, of course, they're compressible themselves. Let's talk about some basics of compressibility effects. First of all, compressibility effects are important and require additional equations, such as, of course, conservation of energy and an equation of state. We've talked about this at length in the beginning of the class, when, of course, we were going over the fluid dynamic equations of motion. Now, we will need some sort of new averaging technique that will be able to handle turbulence modeling and compressibility effects. You might wonder, why don't we just use standard Reynolds averaging? Well, if we do, and include, of course, the variation of density to account for compressibility in a typical flow, then, of course, there'll be many more types of terms which need to be modeled. By approaching the problem with the Favre-Averaged approach, we reduce the number of terms in the modeling, which is already a large number. We still have the closure problem with Reynolds averaging. Of course, it's just much more pronounced because there's way more unknowns than equations. By using Favre-Averaging, we've reduced the number of unknowns relative to the number of equations just by doing a mass-weighted approach. Now, we should know when compressibility effects are important, and the only really way to do that is through experience and physical intuition, through time, and looking at similar flows in previous studies. So it's going to be up to the user before they have a solution to decide if compressibility is an issue. Often the most simple flows, you might look at things just like Mach number and Reynolds number and these types of issues to see if we have it. Generally, flows, as a rule of thumb, of over Mach 0.3 should include, of course, compressibility in the equations of motion. Flows with large and spatial temporal variation of density also require compressibility corrections. The reason I've written this little note here is because you could have a very low Mach number flow, but it might have very large variations of density. Therefore, we would also need to have some sort of compressibility accounted for in the equations of motion and the solver. Now, particular flows that contain shock waves and expansion waves, which are by definition supersonic, require even more additional attention. They may not need necessarily modification of the equations and turbulence models which we're showing, but they would require specialized numerical methods. We already discussed shock capturing in this class, and those same shock capturing methods, like in the visualization section, can also be applied to the solver itself, not just visualization, to account and capture the shocks. Remember, the shocks are very thin, and of course the number of grid points to resolve them would be extremely large. And so we use shock capturing techniques to reduce the number of grid points and also accurately resolve the shocks. This is also a compressibility issue which we must account for. Compressible flows will be those defined where the density changes and they occur, and there are accordingly small pressure changes present. Now, mathematically, we would define a compressible flow as where the fluid parcel does change volume as it moves through the fluid domain. That is, the volume of each fluid parcel changes with time. You see, so the true definition of compressibility has to do with fluid volume of the fluid parcel. It is not to do with density. In fact, the density variation is a weak definition of compressibility in the flow. This is an important point if you progress on in this field. Now, the compressibility effects will have much less impact on the turbulent eddies within a wall-bounded flow or any other type of flow. So the turbulence itself might be considered incompressible while the flow is compressible. Now, for very large Mach numbers, it could be that the turbulence, which is a characteristic and has its own statistics, could also be considered compressible. And so there's a whole area of research and theory on the so-called compressibility of turbulence. In this class, we generally won't look at flows where the turbulence has a compressibility effect because it is a whole new level of difficulty. Nonetheless, the turbulence itself can be compressible, and we call this field and approaches those of compressible turbulence. We now need to introduce the all-important Markovan hypothesis. The Markovan hypothesis is an effect of density fluctuations on the turbulence are small if they remain small relative to the mean density. That is, the fluctuations of density are very, very, very small compared to, say, the mean density. This is the Markovan hypothesis, and of course it has certain mathematical implications in turbulence modeling and the creation of the models and their use, if it is of course true. It is a kind of assumption. One of its implications is that we would only need to account for the non-uniform mean densities, and when computing the compressible shock-free non-hypersonic flows, this might be very important. Some notes about the limitations of the Markovan hypothesis. It would not be useful in flows with significant heat transfer, those with combustion, in free shears where the density fluctuations are extremely large, and is certainly not in the so-called hypersonic boundary layers. That being said, and those are just a few examples, it does not mean we do not necessarily apply the Markovan hypothesis to just general models anyway and run them going forward. They still produce rather good predictive results, with small errors relatively to other assumptions. Now, we would expect the velocity in the turbulent boundary layer to depend on the Prandtl number, specific height ratio, and the following three non-dimensional parameters. So we're really introducing two particular new non-dimensional numbers relative to the first to collapse the turbulent boundary layer. We need to put these physical considerations on a firm theoretical foundation, and that's what we'll do now. So here the y plus is still the same. That's the non-dimensional distance of the wall with friction velocity and viscosity at the wall. You'll now note that we wrote viscosity with sub w denoting it's a wall quantity. Why? Because of course in a high-speed flow or compressible flow, we would expect viscosity to vary with, of course, spatial position, and it's mainly dependent on, of course, temperature. We also then have like a dimensionless heat transfer term and a turbulent Mach number. Let's first talk about the dimensionless heat transfer. The first is the heat transfer through the wall. In the denominator, we have the density at the wall, C sub p, which is a constant specific heat, the friction velocity at the wall, and the temperature at the wall. So we've created another non-dimensional number. The third non-dimensional number is turbulent Mach number. This is not our classic turbulent Mach number where we just take the free stream velocity divided by the free stream speed of sound, for instance, to find the global Mach number. No, we have a Mach number which is simply dependent on the wall friction velocity and the speed of sound at the wall. This also mainly depends on the temperature of the wall, because of course the speed of sound goes roughly as the square root of temperature for most flows in the standard regime. So based on the previous developed mixing length model and the following assumption that the derivative, that is the shear of the velocity as you go away from the wall, will just go as the square root of the shear stress at the wall divided by the density divided by kappa times y. So this is like some assumption of how partial u partial y will go. And from experiments, this assumption is shown to be a very good one. Now, Van Driest argues that by rescaling the velocity according to this complicated empirical model, in a sense, it can actually be collapsed, and it can be rewritten in terms of the law of the wall. This is a very strange form, and of course, a and b are constants. Now, you'll see in this particular equation, if we make this sort of form through a velocity rescale, where we're plotting u sup star instead of u. U plus would be u over u tau. Instead, now we have u sup star over u tau. So u sup star is like this compressible velocity, if you will. We can now rewrite our law of the wall as u sup star over u tau goes as 1 over 0.41 times the natural log of y plus, of course, c. We have now obtained a compressible law of the wall. It's just like the incompressible version in the same form if we use this compressibility correction for rescaling the velocity. It's a brilliant maneuver. C and kappa are still the same type of constants, and thankfully they're nearly the same values as the incompressible boundary layer, but you'll see that they have some dependence. They actually depending on the turbulent Mach number and the heat transfer rate, not dimensionalized. So there's a great difficulty in predicting these free shear layers, boundary layers, and other types of highly compressible flows, and it's much higher, that is the difficulty, than boundary layer cases which are incompressible. In fact, this was the previous case we actually looked at for incompressible flows, but of course you see we're looking at it for compressible flows. Now that we looked at some basic physical considerations, let's turn our attention for the object of the talk today, which is Favre-Averaging. Of course, he was a mathematician, and he looked at the Reynolds average compressible equations of motion, and these resulted in additional correlation terms that have no analogy with the original Navier-Stokes equations. We'll illustrate this through a particular example to make it simple and concrete. Recall that the Reynolds averaging of the density term, and we can substitute it in the equations of motion. So go back to the original Navier-Stokes equations with compressibility, and you would have to realize that we also have to average density. We didn't do this before. And so we would have rho equals rho bar plus rho prime. This is the base value or the time average value plus the fluctuating quantity rho prime. We take each value of rho in all equations and substitute them in. Let's do this, for example, for the continuity equation, which appears here by my cursor. Before we had partial rho partial t plus partial rho u partial x plus partial rho v partial y plus partial rho w partial z equals 0. Now we have, with our substitution, partial t of rho bar plus rho prime plus the expansion of all the other terms and, of course, the second term. I won't read it out. You can look at that yourself. We can find the equivalent Reynolds average continuity equation just as we did before. We arrive at the Reynolds average continuity equation, which is, of course, the second equation on page 8 of this lecture. And you'll find partial rho bar partial t plus partial rho partial xi of rho bar u plus a term, a correlation term, a new one which appears only when we have compressibility of rho u. This will be equal to 0. So you see we've increased the difficulty of the closure problem because now we have this extra term appearing, of course, in the continuity equation. These same types of extra terms also form and apply in other equations. So here's an approximation for the correlations between rho prime and u prime. For closure, we would require that type of term to be modeled here, the last term in the equation on the left-hand side. So the momentum equation, we would also need all other terms. One particular example might be rho prime, ui prime, uj prime. And of course, the time averages those quantities. We can overcome these problems with the density-weighted Favre average. That is, we can eliminate some of these extra closure terms by the careful selection of a weighted average. Let's look at that now. The weighted average of Favre is shown here in the top line of the page. Here, the Nova bar denotes the traditional Reynolds average. And for traditional averaging, we can immediately say that rho bar u tilde I equals rho ui bar. Let's look at the average now. We'll denote Reynolds averaging, the traditional averaging approach with respect to time and no weighting, is with just a bar. So for example, rho ui bar is traditionally simply the traditional Reynolds average. A tilde represents the Favre-Averaged operation on the particular variable. In this case, if we just want to Favre-Average u, we'll take 1 over rho bar, which is, of course, the Reynolds average of density at that particular point in space and time, and let the limit of time go to infinity of 1 over time, and here we have the traditional averaging. But in the integrand of the averaging equation, we have density times, of course, ui. This is what we call a mass-weighted average. Why? Because we've weighted the averaging variable u with density. And of course, we put 1 over rho bar. If we put rho in this equation, of course, we would be reduced to the traditional Reynolds average. We could change u for, say, pressure or temperature, and find mass-weighted quantities. Let's try an example. Say we have rho bar u tilde. This would go as rho ui bar. We could then expand the right-hand side and find this particular form, where we have rho bar ui tilde equals rho bar u, which is another average, mind you, just written without the bar, capital U, plus rho prime ui prime bar. Let's apply the Favre-Averaging technique to the traditional continuity equation from the previous slide. Going Favre-Averaging this equation, of course, we'll still find the same first term, partial rho bar partial t. Why? Because, of course, we're Favre-Averaging or mass weighting the actual density term. The second term now is partial xi of rho bar ui tilde, which is 0. This is amazing and an excellent choice because, as you see, relative to the traditional Reynolds average, we've eliminated one of the closure terms. Therefore, we've reduced the number of closure terms, or that is terms we need to model, or unknown variables in our systems of equation. And this is an excellent choice, which makes of course, mass weighting much easier for modeling. So what has this done? We've essentially treated the momentum per unit volume as a dependent variable rather than the particular velocity like we did before. This can be stated in another way, that the rate of change in momentum per unit volume, not the velocity, will be equal to the sum of the imposed forces per unit volume in the flow. Remember, Favre-Averaging is a mathematical operation which only simplifies the modeling. It does not remove the effects of density on the turbulence. So this way, it's just a simple mathematical operation with no assumptions. We have not really altered our equations in any way except through our averaging approach. If you believe that the statistical approach is correct, then you must believe that this is an approach which is mathematically valid. There are a few more notes on Favre-Averaging. First, it's customary that we always decompose instantaneous velocities into mass average parts and fluctuating parts, as we do, of course, in the first line. So now we would say that the velocity goes as its mass average plus a fluctuating part. We denote the fluctuation about the mass average, which is denoted by tilde, by double prime. So now, primes fluctuate about time averages, double primes fluctuate about mass averages. It's a good thing to remember now. The Favre averages are formed by multiplying by rho and performing a time average, which we just seen. And we can take this traditional Reynolds average and rewrite it as a summation of course, a Favre average and the density times, of course, its Favre average. Now, the averages of the density and fluctuating velocities are always 0. Why is this? Why? Because, of course, averages of density are, in fact, density, no matter if they're mass-weighted or Reynolds average. So we can technically pull out the density in this type of term, and we'll have a fluctuating average, which, of course, is by definition 0. But remember, this average is about the mass, so this term only can be set to 0 because of this reason. The Reynolds averaging of ui double prime will not be 0. Why? Because, of course, it's averaged about density and not, that is, the time average of just the variable. So we could rewrite ui double prime as ui, which is the original velocity component, minus u tilde. Using these equations, we can now eliminate tilde ui. We could write from the previous equation ui double prime, the same left-hand side, with the same first term ui, minus, with a substitution of ui, that's the time average velocity, minus the Reynolds average of rho prime ui prime all over rho bar. Notice we added a rho bar here and here to account for, of course, the mass weighting there in its substitution. The conventional Reynolds averaging will yield an equation like this. Ui double prime bar, that is if we're averaging a fluctuation of a mass average, negative rho prime ui prime bar over rho bar. And of course that will not be equal to 0. You'll see that, of course, right here. And it's not equal to 0. Nonetheless, we would need to try and perform these averaging on the full Navier-Stokes equations. Now, previously in the class, we worked very hard to show you the overview of the derivation of the full Navier-Stokes equations. These should look familiar to you in index notation or Einstein notation. The first equation, of course, is continuity. The second is momentum. And the third is an energy equation for, of course, an internal energy with a kinetic energy. Here, E is the specific internal energy, and we've introduced H as the specific enthalpy. Let's close this equation with, of course, the perfect gas law, P equals rho RT. Then we can define the rest of the variables for this particular set of equations. I've written this particular equation twice. Please scratch it in your notes. Let's try and Favre-average this set of equations. We would substitute Favre-averaging in for velocities, enthalpy, internal energy, temperature. And we would substitute in traditional Reynolds averages for density, pressure, and the heat transfer term. Why? Because of course we can selectively average each variable how we desire. And of course it'll be consistent as long as we're consistent in our mathematics. The benefit of this is we'll have an optimized system of equations for working in turbulence modeling. Let's perform these averages. First, of course, let us look at the continuity equation. This is what you'll receive, just like we showed earlier in this particular slide deck. We'll also have the Favre-Averaged momentum equation and the Favre-Averaged energy equation. Finally, we have the gas law, which takes a slightly different form. Capital P equals rho bar r T tilde. Here we have a Reynolds average of pressure and density and a Favre average of temperature. This is a little bit confusing, of course, because the temperature will be mass weighted and the density, well, it's just the density itself averaged, could be, and of course, static pressure, Reynolds average. Take a few minutes to look through these equations, and you'll see that indeed we have not obtained too many more additional coefficients compared to the traditional Reynolds averaging in the full compressible set of equations. You will note that the only difference between the incompressible version of the RANS equations is the appearance of the Favre-Averaged Reynolds stress tensor. You'll recall the original Reynolds stress tensor had a term like negative rho times the average of ui prime uj prime. Now we have a normalization of the Favre-Averaged Reynolds stress of negative of the average of rho ui double prime uj double prime. So the u's, of course, are mass weighted now. We would divide the whole thing by rho bar, which is the average of density, and find, of course, the Favre-Reynolds average stress. This also has some of the same properties as the traditional Reynolds stress tensor. One, of course, is symmetric, and each term within the Favre-Averaged and Navier-Stokes equations will have unique properties in physics. But it's wonderful it's symmetric because of the same properties. We actually reduce the number of equations or terms that we need to model by 3, because of course it's a 9 by 9 tensor. We could also consider some of the particular correlations of the terms themselves to try and simplify the set of equations. Consider the correlation term between ui double prime and itself. This can easily be written as rho bar k of 1/2 rho ui double prime ui double prime. The correlation between uj double prime and the enthalpy, mass weighted, will be the turbulent transport of heat. And in the analogy to the molecular transport of heat, which we showed earlier, we can write Q of Tj, that is turbulent, goes as rho uj double prime h double prime. So here we've simplified things a bit further in our particular energy equation. We can look and do more analysis of particular terms. For example, the shear stress term with mass weighted velocity fluctuation, and of course the density with mass weighted fluctuation of 1/2 the kinetic energy of mass weighted fluctuations. These two particular terms, which we would need to model, can be physically interpreted as the molecular diffusion and transport of turbulent kinetic energy, respectively. They will indeed represent transfers between the mean kinetic energy and turbulent kinetic energy, and these will arise when we derive the fan's turbulent kinetic energy equation, which is coming. We can find an equation for turbulent kinetic energy simply by multiplying the primitive variables in their form of instantaneous momentum by ui double prime and the particular time average. We can now look at each particular term and individually simplify. We'll do this term by term in the next couple slides. If we look at the first term, we can rewrite that and expand that out as a form of k with this extra correlation. We can look at the second term, which is the convection term, and make simplifications using all the arguments and mathematical identities which we showed earlier in this very class. We also have the traditional pressure gradient and viscous terms. I'll let you read through these yourself and see if you can understand each step of the simplifications. It's a good exercise so you can fully understand mass weighting of Favre-Averaging. Now, we would substitute these terms term by term and find the so-called Favre-Averaged turbulent kinetic energy equation. This, you'll see, is an exact equation based on Favre-Averaging, and that's quite amazing because we have not made any additional assumptions. All the things we've shown are simply mathematical identities of statistics associated with mass-weighted averaging. Here's the full form of the turbulent kinetic energy equation of Favre-Averaged Navier-Stokes equations. Here, once again, on the left-hand side, we have a density terms times partial k partial t plus rho bar uj tilde partial k partial xj. And we have terms on the right-hand side, which corresponds very similarly to the terms, of course, in the original RANs. You'll notice that once again, this is a partial differential equation which is tracking turbulent kinetic energy K, very much the same type of turbulent kinetic energy which we looked at previously. Now, the last two terms here are new if you've been paying careful attention compared to RANs, and they are, of course, the pressure work and pressure dilatation. If the incompressible form of the equations is recovered, then we would simply set these two particular terms to 0, and of course our density would become constant and we would recover exactly the original RANs equations. So the RANs equations can be recovered from the Favre-Averaged equations by eliminating these types of terms which only appear due to compressibility, and they'll eliminate themselves essentially if you solve for the flow field correctly, and you wouldn't have to worry about it. It'd be a lot more computational work. Now, the last two terms on the right-hand side can be interpreted in a little bit different ways. They might be seen as the mean energy equation, which is the molecular diffusion and turbulent transport of turbulent kinetic energy. The Favre-Averaged dissipation rate can also be found. Recall our earlier definitions of dissipation found through RANs and their formal definition. They all look very similar, but have very, very slightly different values, within much less than 1%. The first one is just the mass-weighted, of course, dissipation. It'd be rho bar of dissipation goes as 1/2 the shear stress times the bar of partial ui double prime partial xj plus uj double prime partial xi. This can rewrite in compactly as Tij Sij double prime. Recall our definition of Sij. We can also derive, in a similar fashion, the Favre-Averaged Reynolds stress equation. We derived, of course, turbulent kinetic energy directly, but here we'll show the more general term, which of course is a tensor equation for the Favre-Averaged Reynolds stress. This is a little bit different than the traditional Reynolds stress equation. Here we have partial t of rho bar ta ij, which is the Favre-Averaged Reynolds stress, which we just defined, equals all very similar terms on the right-hand side. You'll notice that there's a particular production, dissipation, and the same triple correlation type terms which we had in the RANs equations. If you don't recall these types of forms in the equations, go back and look now. But they have almost the same form, of course, except now they're Reynolds averaged. We've done a lot of mathematics behind the scene here to try and recover these particular variables. Now, let's go through and summarize all the Favre-Averaged equations, which are found just like the RANs equations, but with a little bit of extra mathematical statistical operations, and of course the fact that we've mass-weighted the equations, and you'll see that they have almost a similar form to the original RANs equations. We have continuity, momentum, energy, a turbulent kinetic energy equation, and of course in the previous slide we've shown the Reynolds stress equation. These are really important equations for, of course, formation of turbulence closures for compressibility. This is all, of course, done for you, and there's many types of models that try and close this form of the equations. But if you're working in high-speed aerodynamics, and then you're perhaps in aerospace engineering and doing CFD, these are the actual equations we're really solving, plus all the different types of closure schemes. We'll look at some of those results coming up in this class. So we've worked very hard and outlined the development of the Favre-Averaged Navier-Stokes equations, which of course will be able to account for compressibility in a very efficient manner relative to the original RANs equations. Let's make some notes now about their closure, because the equations themselves are not useful without some sort of turbulence model. Of course, in addition to the unknown density now, which is another equations and the most important field variable, often the first field variable is density, we'll have additional correlations involving density. We must, of course, model and find and close this system of equations because we have more unknowns than equations. This is the closure problem for the FANS equations versus RANS equations. It is still part of classical turbulence modeling and theory. So we'll try and find this particular closure for the mass-averaged Reynolds stress tensor and heat flux vector. Those are the two terms which we focus on most. We'll examine these and we'll look at the most basic closure for FANS, Favre-Averaged Navier-Stokes. And we'll use a particular philosophy. Let's look at these 3 points together because they're so important. We will view all closure approximations should approach the proper limiting value for Mach number and density fluctuations tending to 0. So that is, as Mach number decreases and density fluctuations decrease towards the mean value, we should actually recover the incompressible type result and solutions. Second, all the closure terms should of course be written in proper tensor form. This will help us track our mathematics through the work. And it's a good time to go back and review the tensor mathematics portion of the class if you don't recall some of the things we're seeing. And they will not be dependent on a specific geometric configuration, which of course is the advantage of tensor mathematics. Finally, we will view all closure approximations should be dimensionally consistent and invariant under Gaussian transformations. This is more of a mathematically rigorous point. Let's first look at the Reynolds stress tensor. Now for 0, 1, and 2 equation models, we can develop all these types of models for Fans equations just like Rand's. We will still use and approximate the Boussinesq approximation, but here's for compressible flows, not for necessarily more general form. The Boussinesq approximation for compressible flows will be rho bar of T tau ij will of course be the definition of Fans stress tensor, as 2 times some eddy viscosity times that stress tensor minus 1/3 of the trace of velocity gradient times the Kronecker delta function minus 2/3 of rho bar k delta ij. So this looks very familiar to you, hopefully. And of course, you'll see that this term right here, if it's an incompressible flow, will go to 0. Why? Because it's very much like summing over k, partial u tilde partial x plus partial tilde partial y, plus partial tilde partial z is 0. So as this compressible Boussinesq approximation goes to, of course, the incompressible limit, lower Mach numbers and fluctuations in density, then we actually, of course, recover the traditional Boussinesq approximation. So it's a great choice. And it's found in mathematical theory, so that's good. The turbulent heat fluctuation vector will be viewed next, and this will follow the same approach for the incompressible flows which we showed earlier. And we will approximate that heat transfer rate with some particular turbulent Prandtl number, which might be set as 0.9 or 0.91 in most turbulent flows. To understand this equation, you really need to take a convection heat transfer class to justify it. There's something called Fourier's law of heat conduction, which we basically use to approximate through dimensional analysis this particular triple correlation term. Other terms let's look at are the particular molecular diffusion and turbulent transport terms, the dilatation and dissipation term, and we would split this particular terms into 2 components. There are many additional terms in the compressible flow closure for the Fans equations. I've listed some of these here in some detailed slides. I'll let you take a few minutes to read them yourself. You'll see that the concept and difficulty of modeling these terms in the Fans equations takes a lot of time to understand, and of course even more time to create these particular models. These are often discussed in depth in turbulence modeling classes in graduate school. For an introductory subject to CFD for now, it's best just to read through them and try to understand the entire CFD process, and then go into a particular field that interests you. I do recommend taking an advanced class in turbulence and turbulence modeling so you can understand the particular dynamics of some of these modeling of course, the correlation terms. As an example, so you can understand the process better, we're going to now look at some particular compressibility corrections for something much simpler and less general, which of course is the mixing layer compressibility corrections. So these would be used opposed to the Fans closure, the full Fans closure, as a correction of the incompressible flow equations. We'll look at these compressibility corrections now. So some CFD codes use these types of compressibility equations and corrections versus trying to move forward through the whole Fans and closure processes and implementation, which is of course much more mathematically rigorous and robust and creates better predictions sometimes, if not usually, relative to the modification of the base equations such as k omega. So for an example, so you can understand this in the big picture, we'll look at modifying the k omega model. First, let's make a change of variables. We'll say epsilon sub s goes as beta sup star of omega k. This is very much like our original equations, relating dissipation with specific dissipation, and of course turbulent kinetic energy. We'll have a mixed equation now for, if it's a k omega model, we would take the omega equation for rho bar of d omega dt goes as the right-hand side of rho bar over beta sub star, which is a function now, times turbulent kinetic energy with a tracking equation between the difference between dissipation and the turbulent kinetic energy. This is a new type of equation which is mixed. It's not really unique in a sense because of course we derived it from existing equations. It's not really helping too much in our closure. It's a replacement equation based on substituting 3 other equations. Look at the particular closure coefficients now. These are simply made and calibrated. Now, based on this mixed equation, there's 3 people who came along and proposed coefficients and functional forms for, of course, beta star, beta, and f, and all these other terms. These are generally household names in the field of CFD and turbulence. The first is by Sarkar, Zeeman, and Wilcox. Based on this simple correction and replacement of an equation in a k omega model with a mixed model, we can now calibrate the terms and see how it does on a particular flow. Here we see the prediction of a compressible mixing layer. That is a shear layer, if you will, with compressibility effects. The x-axis represents convective Mach number. The y-axis represents, of course, some spreading rate relative to a base spreading rate. That is the rate at which the shear layer spreads because of the turbulent mixing. The dots are experiments. And of course, these 3 particular models show the results. The dashed line is the classic k omega model, which was found through incompressible formulation. The long line and the dashed line are of Wilcox and Sarkar. You can see that the original model completely misses the experimental data. It's incompressible and can't account for compressibility. At higher convective Mach numbers, say 0.4 and higher, you can see there's a large divergence between experiment and, of course, what would be the incompressible result. The compressibility corrections all worked fairly well and captured the data, and the overall trend all the way up to a convective Mach number of 2. You can see as all these models approached the convective Mach number 0, that is the relative Mach number between the compressible shear layers, that they approach the incompressible result. So they still capture and, of course, decay the compressibility effects as Mach number goes to 0. That's a quality of a model which must occur, as I showed in point number 1. Let's now look at the compressible turbulent boundary layer. There are some particular differences between the predictions and the composite profiles in the compressible and incompressible cases. Let's illustrate this now through 2 particular figures. The first figure is at Mach 4.5. The second figure is Mach 10.3. That's the incoming Mach number of the particular boundary layer and experiment. The experiments are shown as symbols, circles and squares on the 2 plots respectively. Once again, the y-axis is y plus. Remember, that's non-dimensional velocity. The x-axis, of course, is non-dimensional distance to the wall. Now, we've shown 2 particular CFD predictions. The one is the solid line, which is k omega model. The second one, the dashed line, represents the Chien K epsilon model. You can see here that the Chien K epsilon model is actually an incompressible model. The Chien K epsilon model is a classic model which is implemented in many CFD codes. It over-predicts the experimental results. The compressible form of the K omega model is very predictive along especially the log layer of Mach 10, but overpredicts the defect layer at high Y plus values or the outer layer region. It's very good and predictive and finds excellent results for, say, a Mach 4.5 flow. Why is that? Well, Mach 4.5 is really on the edge of the supersonic regime. Once we get to Mach 5 and higher, we're really entering a hypersonic regime where other types of physics are occurring which are not accounted for in this particular closure. Additional closure coefficients or modifications and additional equations to track physics would be required at the Mach 10.3 flow. Let's look at another application. Here's the so-called Wilcox compressibility correction on surface pressures for Mach 3 flows into a compression corner. This is simply a corner flow where the flow comes and is turned by a wall in a corner. It might have a very small angle. Here we have particular distances along the wall. 0 represents the corner. Higher values of x over delta represent distance downstream. Negative values represent distance upstream. The y-axis on the left plot is the pressure at the wall divided by the ambient pressure. On the right, we have skin friction at the wall times, of course, 10 to the third. Experiments of Settles, Voss, and Boganoff are shown as circles. And of course, we show two particular predictions of the k-omega model over a 24-degree compression corner. One case has the value psi sup star as a solid line, and the other one has a dashed line for 3/2 and 0. Of course, psi sup star of 0 here indicates a incompressible or no correction case. 3/2 is the correction factor, which goes back into the compressibility correction model, which we discussed just now. You can see that the results of the compressibility correction are much improved. Here's another example, which I'll let you look through, for, of course, a Mach 9.4 flow past a 40-degree cylinder flare. Once again, there's experiments comparing pressure and heat transfer rates on the cylinder as a function of distance on the cylinder flare. Dashed lines are, of course, a simple two-layer model, which we discussed previously in the two-equation class, and the solid line, of course, is a k-epsilon model with compressibility corrections. In all these codes, they have, in these results you're seeing here, you're seeing incompressible formulations that are being altered by compressibility corrections. How is that done? They essentially would take the incompressible formulation using the Rand's closure and add in two more empirical terms to represent the pressure dilatation and the pressure work of the turbulent kinetic energy equation. So if the major difference between the incompressible and compressible flows rely on these two terms at the end of the turbulent kinetic energy equation, they could just try and do a compressibility corrections to their current formulation by subtracting and adding the two terms in particular. This is a little bit easier and also easier to program for a programmer to put in the two additional terms from an already established and validated Rand solver. Let's summarize and make some concluding remarks about our class today. I hope that you got a general idea of what the Favre-Averaged and Navier-Stokes equations are, and of course how they're formulated, and just a tip of the iceberg of their closure, which is an extremely advanced subject which would require knowledge of a lot of physical fluid dynamics and mathematics that are a little bit beyond this current class. But I hope you get some interest in it and can try and progress in this field if you have some liking for it. Compressibility terms in often many CFD codes are turned on and off. By turning them on and off, you're essentially adding those two terms, which I just pointed out, in the traditional incompressible formulations. Some turbulence models are implemented and based on the full Favre-Averaged Navier-Stokes implementation. It's important that you know which one you're actually using. We tried to discuss and point out important physics of the particular compressibility. We also discussed reasons for using the Favre-Averaged equations. Remember, the major reason is we have less closure coefficients than the traditional Rand's approach applied to the compressible form of the equations in motion. We also looked at, just very briefly, a very simple correction for a mixing layer. The actual compressibility corrections going in the code are more complicated because they try and handle more general flows. And we just showed a few cases of what might happen if you're applying the incompressible formulation without compressibility corrections or not applying compressibility at all to high-speed flows. You're going to be creating results which are not predictive. Next time, we're going to turn our attention to a different type of simulation that is not based on the Rand's or FAN's types approaches. These are more used today in either research or emerging from research and becoming useful in industry. They're very, very computationally expensive. The first one is called direct numerical simulation. Direct numerical simulation simply means that we are solving and integrating the full set of Navier-Stokes equations directly with no turbulence modeling or closure. The second set is a new kind of turbulence model, which has become very popular in the last 2 decades. Of course, it's called large eddy simulation. The objective is to resolve and simulate through temporal integration the largest scales of turbulence and model through turbulence modeling the smallest scales. Next class, we'll talk about both these approaches and look at some examples. Thank you very much for your time today. I'm Professor Steve Miller.